Tests of Properties of Adhesives examines how adhesive performance is evaluated using standard test methods for peel, shear, impact, fatigue, durability, and biological resistance. In academia and research, this topic is important for understanding bonding mechanisms, comparing formulations, and improving material performance. In industry, it supports product design, quality control, process optimization, and safe material selection for real service conditions. In business, reliable adhesive testing reduces failure risk, improves customer confidence, supports certification, and strengthens market competitiveness. Outline. Introduction. Definition of adhesives. Types of adhesives. Application of adhesives. Why is adhesive testing necessary? Surface and specimen preparation. Tests of properties of adhesives. Notable industries globally that are involved in adhesive production. Introduction. Goal. This study explains what adhesives are, where they are used, why they are tested, and how the main ASTM adhesive test methods are selected and interpreted in practice. Audience: undergraduate/postgraduate students, lab technologists, QA/QC officers, production engineers, materials scientists, and adhesive formulators. Main message: no single adhesive test tells the whole story. The test must match the substrate, joint geometry, loading mode, and service environment. ASTM itself lists many adhesive standards because adhesive performance depends on properties such as adhesion, shear strength, and modulus, and because bonded joints can involve metal, wood, plastic, and composites. Definition of adhesives. An adhesive is a substance that joins materials together by surface attachment and resists their separation. Adhesive bonding is often chosen because it can join similar or dissimilar materials without drilling, bolting, or welding, and it can help distribute loads across a joint rather than concentrate them at fastener points. This is why adhesive standards exist for metals, plastics, wood, and composites. The three basic terms below are important in the study of adhesives. Adhesive equals bonding material. Adherent equals material being bonded. Bond line equals adhesive layer between substrates. Types of adhesives. A. Classification by source. A. Natural adhesives and A. Synthetic adhesives. B. Classification by curing or bonding mechanism. Water-based/dispersion adhesives. Solvent-based adhesives. Hot melt adhesives. Pressure-sensitive adhesives and reactive adhesives such as epoxies, polyurethanes, acrylics, and anaerobic systems. C. Classification by engineering function. Non-structural adhesives for light-duty attachment and structural adhesives for load-bearing assemblies. Where adhesive bonding matters, application of adhesives. Packaging and flexible laminates. Automotive interior and body assemblies. Aerospace sandwich panels and metal/composite joints. Electronics and appliance assembly. Construction and wood products. Medical and consumer products. Industrial point to note. The application determines the required test. A flexible laminate is usually peel critical, while a metal overlap joint is usually shear critical, and a structural assembly may also require fatigue and durability testing. Why is adhesive testing necessary? This section is important for both academia and industry. Main points: to compare adhesive formulations under controlled conditions, to qualify materials for a specific product, to study surface treatment and bond preparation effects, to support quality control and process control, to evaluate durability under heat, humidity, water, or cyclic loading. Surface and specimen preparation. 1. ASTM D2651, preparation of metal surfaces for adhesive bonding. 2. ASTM D2093, preparation of plastic surfaces prior to adhesive bonding. Preparation of metal surfaces for adhesive bonding, ASTM D2651. ASTM D2651 is a guide for preparing wrought metal surfaces before adhesive bonding, with the aim of producing a clean, active, and reproducible surface that promotes strong and durable adhesion. It applies to several engineering metals, including aluminum alloys, stainless steel, carbon steel, titanium alloys, magnesium alloys, and copper/copper alloys, and notes that the exact preparation method should be selected according to the metal type and the agreed qualification or quality control procedure between manufacturer and user. It does not cover cast metals. In practice, the process begins with surface cleaning and degreasing to remove oil, grease, dirt, and other contaminants that would interfere with wetting and bonding. Depending on the metal, this may be done by vapor degreasing, alkaline cleaning, detergent cleaning, or other suitable solvent-based cleaning methods. After degreasing, the surface is commonly given a mechanical treatment such as abrasion, sanding, grit blasting, brushing, or scouring to remove weak surface films and increase surface uniformity. ASTM D2651 indicates that both mechanical and chemical techniques are used, and that the sequence depends on the metal system. The next step is usually a chemical or electrochemical treatment designed to activate the surface and create a more bondable oxide or conversion layer. For example, the guide lists etching, anodizing, electrochemical cleaning, and related treatments for aluminum, acid etching options for stainless steel and carbon steel, etching or anodizing for titanium, corrosion-conscious preparation for magnesium, and specific chemical treatments for copper alloys. These treatments are intended to improve bond reliability, not merely surface cleanliness. After treatment, the prepared metal is typically rinsed, dried, and protected from recontamination before adhesive application. Overall, ASTM D2651 emphasizes that successful adhesive bonding depends not only on the adhesive itself, but also on a carefully controlled and metal-specific surface preparation procedure. ASTM D2093, preparation of plastic surfaces before to adhesive bonding, process summary. ASTM D2093 is a standard practice for preparing plastic adherents before adhesive bonding. Its purpose is to reduce surface variability caused by differences in plastic manufacturing and thereby make adhesive test results more consistent and comparable. The standard makes clear that it covers only the pretreatment of the plastic surface. It does not cover specimen fabrication, test conditions, or result evaluation, which are addressed in other ASTM test methods for specific materials. It is also presented as a starting point for evaluating surface preparation techniques rather than a guarantee of optimum adhesion in every industrial application. In practice, the process begins with cleaning the plastic surface to remove dirt, grease, mold release agents, and other contaminants that can prevent proper wetting by the adhesive. ASTM D2093 indicates that physical treatments such as sanding and solvent wiping are used to remove glossy surface layers and surface contamination. This step helps expose a more uniform and bondable surface. After cleaning, some plastics may require chemical treatment to improve adhesion further. ASTM D2093 notes that chemical methods can alter the outer polymer surface itself and improve its adhesion characteristics. Examples named in public summaries of the standard include treatments such as sulfuric acid, dichromate solution, and sodium naphthalene complex, depending on the plastic type. These treatments are used selectively, since not all plastics respond the same way and the standard does not claim to cover every plastic or every available preparation method. After pretreatment, the surface should be handled carefully to avoid recontamination before bonding. Overall, ASTM D2093 emphasizes that successful bonding of plastics depends heavily on proper surface preparation, but the exact method should be chosen according to the plastic material, adhesive system, and intended test or application. Adhesive test methods to be considered. The adhesive test methods to be considered are: 1. ASTM D1876 T-peel test. 2. ASTM D3165 shear by tension loading of single lap joint laminated assemblies. 3. ASTM D905 shear by compression loading. 4. ASTM D950 impact strength of adhesive bonds. 5. ASTM D2919 durability of adhesive joints stressed in shear by tension loading. 6. ASTM D3166 fatigue properties in shear by tension loading. 7. ASTM D4300 standard test methods for ability of adhesive films to support or resist the growth of fungi. ASTM D1876 T-peel test. Testing condition. ASTM D1876 measures the relative peel resistance of an adhesive bond between two flexible adherents arranged as a T-shaped specimen and loaded in tension. Meaningful comparison is obtained only when specimen construction, bond width, adhesive cure, and test conditions are kept identical. A common laboratory setup uses bonded strips about 25.4 mm wide and about 300 mm long, with free ends left unbonded for gripping. Testing environment. Testing should be carried out in a controlled laboratory environment after all specimens are conditioned the same way. Temperature, humidity, dwell time after bonding, and substrate/adhesive conditioning should be reported because they can change peel response, especially for thin films, laminates, and soft adhesive systems. Testing apparatus. A universal testing machine, tension testing machine, a properly selected load cell, opposing tensile or pneumatic side action grips, and computerized data acquisition software are required. The method records load versus head movement or distance peeled. A rule or caliper is also needed to measure specimen width accurately. Procedure of testing: prepare a bonded flexible to flexible panel, cut replicate T-peel specimens, and bend the unbonded tabs back to form a T. Clamp one tab in the upper grip and the other in the lower grip so the bond line stays centered in the loading axis. Peel the specimen at constant crosshead speed, commonly 127 mm per minute, and continuously record the force. The average load is taken over the specified peel length after the initial peak. Test parametered unit calculations to obtain test parameter. Primary outputs are initial peak load, average peel load, minimum/maximum peel load, peel strength, and failure mode. If F average is the average peel load, N, and B is the specimen width, millimeter, then peel strength, P, equals average force divided by the specimen width, B. ASTM D3165, shear by tension loading of single lap joint laminated assemblies. Testing condition: the method is a comparative single lap shear test for adhesively bonded laminated assemblies under tensile loading. A bonded overlap is prepared under controlled adhesive application, surface preparation, cure schedule, bond line thickness, and specimen geometry. Loading is applied to failure at a controlled rate. ASTM D3165 is intended mainly for comparative evaluation and in-process quality control rather than direct structural design values. Testing environment: specimens are conditioned and tested under a stated laboratory atmosphere, and any special preconditioning used for the study should be reported. Environmental history before testing, such as ambient storage, heat aging, or moisture exposure, must be controlled because adhesive strength is sensitive to temperature, humidity, surface cleanliness, and cure state. Testing apparatus: a universal testing machine with a calibrated load cell, fixed/self-aligning grips, and a constant crosshead speed is used. Standard single lap joint specimens are gripped axially so that tensile force is transferred through the overlap region in shear. Measuring devices include force, extension/crosshead displacement, overlap length, specimen width, and bond area measurements. Procedure of testing: prepare adherents, clean/treat surfaces, apply adhesive, assemble the prescribed overlap, and cure as specified. Measure width and overlap length, mount the specimen carefully in the upper and lower grips, and align it to minimize twisting. Apply tensile load continuously at the specified rate until joint failure. Record the maximum load and observe the failure mode as adhesive, cohesive, substrate, or mixed failure. Test parameter, unit, calculations to obtain test parameter. Primary parameter, apparent shear strength, usually reported in MPa, Newton per square millimeter, or psi. First, obtain the bonded shear area, A equals overlap length times specimen width. Then compute apparent shear strength, tau equals maximum force divided by area, where Pmax is the maximum load at failure in newtons, or pounds force. Supporting results may include load, displacement behavior, and percentage or description of failure mode. ASTM D905, shear by compression loading. Testing condition. ASTM D905 measures the comparative shear strength of adhesive bonds used mainly for wood and similar materials under compression loading. Standard bonded block specimens are prepared with controlled adhesive spread, cure schedule, bond area, grain orientation, and loading geometry. The method is comparative. Measured strength may be influenced by wood strength, wood failure, specimen quality, and the shear tool design. Testing environment. Specimens are conditioned to a defined moisture/temperature state before the test. Laboratory testing is typically performed at ambient room conditions after conditioning, while moisture content, conditioning history, and any wet or dry exposure must be reported because wood and adhesive response are environment sensitive. Testing apparatus. A calibrated universal testing machine or compression frame, a suitable load cell, ASTM D905 compression shear fixture/shear tool, a specimen alignment seat, and data acquisition software are required. Supporting tools include cutting/jig equipment for bonded wood blocks, thickness/width measuring devices, and conditioning facilities. Procedure of testing. Prepare and bond matched wood blocks, cure as specified for the adhesive system, and condition the specimens. Place the bonded block in the D905 shear fixture so that compressive loading acts parallel to the glue line and induces shear across the bonded area. Load at the specified constant crosshead/position rate until failure, then record maximum load and observe wood, adhesive, or mixed failure. Test parameter/unit/calculations to obtain test parameter. Primary result, apparent shear strength, tau equals maximum force divided by area, where tau is in MPa, or Newton per square millimeter. Maximum pressure is the maximum load in N, and A is the bonded shear area in square millimeters. If the area is rectangular, A equals B times L, where B is the bond width, and L is the bond length. Report maximum load, calculated shear strength, specimen dimensions, conditioning state, and observed failure mode or percent wood failure when relevant. ASTM D950, impact strength of adhesive bonds. Testing condition. ASTM D950 determines the comparative impact strength of adhesive bonds in shear using standard bonded metal blocks under specified conditions of surface preparation, bonding, conditioning, and impact testing. The adhesive manufacturer should state the surface preparation method, mixing instructions, application thickness or spread, assembly or open time, pressure, cure time and temperature, and any conditioning required before test. Testing environment. Unless another condition is specified, specimens are conditioned in a room or desiccator maintained at 23 plus or minus 1.1 degrees Celsius and 50 plus or minus 2% relative humidity. A saturated calcium nitrate solution may be used in a desiccator to provide approximately this humidity level before impact testing. Testing apparatus. The apparatus is a pendulum-type impact machine with a hammer velocity of 3.4 meters per second, 11 feet per second. It includes a flat striking head slightly wider than the specimen, a solid steel jig bolted firmly to the machine base, and a vise or bolts that hold the jig rigidly during impact. The jig contains a tightening screw so the specimen sits flush and does not overturn when struck. The striking face should hit as close as possible to the adhesive line, preferably within about 0.79 mm, 1/32 inch. Machine calibration guidance is referenced to ASTM E23. Procedure of testing: prepare and bond metal-to-metal specimens in accordance with the adhesive manufacturer's instructions. Steel is preferred for high-impact strength adhesives to reduce specimen deformation. The common standard specimen uses a 25.4 by 25.4 mm bonded block joined to a 25.4 by 44.5 mm block. If machine capacity is limited, the square block may be reduced, but the actual bonded area must be reported. After conditioning, mount the specimen in the jig with the impact face square and flat, perpendicular to the bond line and parallel to the pendulum striking face. Apply one blow at the point of maximum hammer velocity and record the absorbed energy required to fail the joint. Test replicate specimens and report the average. Test parameter/unit/calculations to obtain test parameter. The principal result is impact strength, also called impact value. It is the absorbed energy at failure divided by the bonded area, where I is impact strength, E is absorbed energy, with unit in joule, and A is bonded area in square meter. The SI reporting unit is joule per square meter. Inch-pound reporting may also be expressed as foot-pound force per square inch. For the common 25.4 by 25.4 mm bond area, A equals 6.4516 times 10 to the power of -4 square meter. So the measured pendulum energy is divided by this area to obtain impact strength. ASTM D2919, durability of adhesive joints stressed in shear by tension loading. Testing condition: ASTM D2919 assesses the durability of adhesive lap shear joints while they remain under sustained shear by tension stress and are exposed to air, humid air, water, aqueous solutions, or other selected environments at controlled temperature. Test joints are prepared as good quality lap joints, commonly following D1002 practice except for the D2919 specimen dimensions, and the applied stress is chosen as a defined fraction of dry lap shear capacity. Testing environment: exposure may be in laboratory air, air in equilibrium with specific solutions, liquid water, aqueous media, other fluids, or outdoor weathering conditions. Temperature, relative humidity, immersion medium, and exposure duration must be stated because time to failure decreases as stress, temperature, and humidity rise. Outdoor weathering racks in accordance with Practice D1828 are recommended for natural exposure studies. Testing apparatus: required equipment includes the ASTM D2919 durability fixture, a testing machine or other loading device capable of applying measured compressive load with force accuracy of about plus or minus 1% in accordance with Practice E4, a suitable loading base, and the chosen environmental exposure system such as rack, chamber, bath, or solution container. The ASTM adjunct provides the detailed fixture drawings. Procedure of testing: bond the lap joint specimens, cure and condition them, then mount each specimen in the D2919 fixture. Use the testing machine to compress and set the spring-loaded fixture so the joint is placed under the required sustained tensile shear load, lock the assembly, and transfer it to the selected environment. Maintain exposure until bond failure or the planned endpoint, while recording the applied stress level, temperature, humidity or medium, and exposure time. Test parameter/unit/calculations to obtain test parameter, primary durability result, time to failure, TF, reported in hours or days at a stated stress and environment. Applied nominal shear stress is calculated as tau equals force divided by area, where tau is in MPa, or Newton per square millimeter, P is the sustained tensile load in N, and A is the bonded overlap area in square millimeter. For a rectangular overlap, A equals B times L, where B is the specimen width and L is overlap length. Results are often reported as time to failure versus stress, temperature, or humidity, together with surviving specimens at the test end. ASTM D3166 Fatigue properties in shear by tension loading. Testing condition: ASTM D3166 measures the fatigue behavior of adhesively bonded metal-to-metal lap joints in shear by cyclic tension loading under specified specimen preparation, loading, and test conditions. The method uses a standard bonded specimen. When adherent thickness is not otherwise specified, metal sheets about 1.63 mm (0.064 inches) thick are commonly recommended. Results are comparative and depend strongly on adhesive, adherent, overlap geometry, surface preparation, cure, load ratio, and frequency. Testing environment: testing is usually carried out after curing and conditioning the bonded metal specimens at a stated laboratory temperature and humidity, although other controlled thermal environments may be used if required by the material or product specification. The conditioning history and test environment must be reported because fatigue life is sensitive to temperature, moisture, and any prior aging of the bonded joint. Testing apparatus: required equipment includes a calibrated fatigue testing machine capable of applying repeated tensile loads at controlled amplitude and frequency, properly aligned grips or fixtures for the single lap metal specimen, a load cell and cycle counter, and recording software for load, displacement, and cycles to failure. Ancillary tools include specimen preparation equipment, surface preparation materials, and dimensional measuring devices. Procedure of testing: prepare, bond, cure, and condition the metal lap shear specimens according to the selected adhesive system and specimen specification. Mount the specimen carefully in the upper and lower grips so the overlap lies between the grips and axial cyclic tension produces shear in the adhesive layer. Apply the selected cyclic load program at the required frequency and continue until bond failure or the planned run-out limit, while recording maximum and minimum loads, frequency, and total cycles sustained. Test parameter/unit/calculations to obtain test parameter. Main fatigue results are cycles to failure, NF, in cycles, or an SN relation based on apparent shear stress versus number of cycles. Apparent maximum shear stress is calculated as max equals maximum force divided by the area, and minimum shear stress as min equals minimum force divided by the area, where stress is in MPa, or N/mm superscript 2, load P is in N, and bonded area A is in square millimeter. For a rectangular overlap, A equals B times L, where B is specimen width and L is overlap length. The stress range is delta tau equals maximum force, minimum force, divided by area, and the load or stress ratio may be reported as R equals maximum force divided by minimum force. ASTM D4300 Standard test methods for ability of adhesive films to support or resist the growth of fungi. Testing condition: ASTM D4300 evaluates whether an adhesive film inhibits or supports fungal growth on agar plates. Two substrates are used: potato dextrose agar (PDA), which promotes fungal growth, and mineral salts agar (MSA), which is less favorable and mainly shows growth occurring on the adhesive film itself. The method includes a procedure for low-viscosity adhesives and an alternative procedure for mastic-type adhesives. Testing environment: testing is carried out in a sterile microbiology laboratory using correct aseptic technique. Cultures are propagated on PDA at 25 plus or minus 0.5 degrees Celsius for at least 10 days or until full sporulation, and incubation chambers capable of 25 plus or minus 0.5 degrees Celsius or 35 plus or minus 0.5 degrees Celsius are used as required by the selected procedure. The method is not intended for water-soaking conditions because water-soluble biocides may leach from the bond line. Testing apparatus: required apparatus includes a laminar flow biological safety hood, constant temperature chamber/incubator, sterile petri dishes, about 150 mm diameter, hemocytometer for spore counting, Pasteur pipettes, glass rods, refrigerator, jars, filter discs/paper assay discs, and standard sterilization equipment used in microbiological laboratories. A chromist laboratory spray unit is listed for one of the procedures. Procedure of testing: prepare PDA or MSA plates to about 3 mm depth and sterilize media according to microbiological practice. Prepare fresh fungal cultures, harvest spores in sterile water containing 0.05% sorbitan monooleate polyoxyethylene, and adjust the inoculum to 1.0 times 10 to the power of 6 spores/ml with a hemocytometer. Prepare the adhesive sample as supplied or as mixed per manufacturer instructions. Form the adhesive film on the specified support. Inoculate the test system with the selected fungus or mixed culture. Incubate under controlled temperature, and compare fungal growth on the adhesive surface and adjacent agar with simultaneously run controls. Test parameter unit calculations to obtain test parameter. The principal result is resistance or susceptibility to fungal growth, reported qualitatively or semi-quantitatively from visible colonization of the adhesive film and surrounding agar. Where a clear no-growth halo is produced, the zone of inhibition, ZI, is reported in millimeters. A common calculation is ZI equals D underscore total D underscore specimen /2, where D underscore total is the overall diameter of the clear zone, including the specimen, and D underscore specimen is the specimen diameter. The inoculum concentration is reported as spores/ml, typically 1 million spores/milliliter. Below are industries that are into the commercial production of adhesives across Europe, America, Africa, and Asia. Europe. Henkel Adhesive Technologies, Düsseldorf, Germany. Henkel's adhesive business is based there, and its portfolio includes Technomelt PUR polyurethane reactive hot melt adhesives and Loctite epoxy adhesives. Sika AG, Bar, Switzerland. Sika produces adhesive systems including polyurethane, silane-terminated polymer, silicone, epoxy, acrylate, hot melt, and water-based adhesives. Its Sikaflex line is especially known for one-component PU/STP adhesive sealants. Jowett SE, Detmold/Elsterau, Germany. Jowett makes hot melt, dispersion, solvent-based, and reactive adhesives. Its Elsterau site specifically notes manufacturer of hot melt and dispersion adhesives. America. H.B. Fuller, Mesquite, Texas, USA. H.B. Fuller states that its Mesquite plant specializes in manufacturing hot melt adhesives. Across its portfolio, it also supplies water-based, cyanoacrylate, urethane, epoxy, solvent-based, and solventless adhesives. I. Franklin International, Columbus, Ohio, USA. Franklin says its manufacturing facility operates at its headquarters in Columbus, and its businesses include construction adhesives, flooring adhesives, woodworking glues, and manufacturing adhesives. Its multi-bond line includes cross-linking PVA wood adhesives. Bostik Canada Limited, Bécancour, Quebec, Canada. Bostik Canada lists this location and offers adhesive lines such as Purethane water-based acrylic polyurethane dispersion laminating adhesives and 1- and 2-component polyurethane adhesives. Africa. Yalkalin/Bostik South Africa, Cape Town, South Africa. The company lists its Cape Town head office and sells PVA wood adhesives such as alkaline cold glue, epoxy adhesives such as Epoxy Bond, and polyurethane adhesive/sealants such as Alcoflex. ABE Construction Chemicals, Durban Factory, South Africa. ABE lists a factory in Durban and produces epoxy adhesives such as Epidermix 372, polyurethane modified epoxy structural adhesives such as Epidermix 350, and bitumen woodblock adhesives such as Gripablock. Sika Egypt, El Obeir City, Egypt. Sika Egypt's contact details point to El Obeir City, and its industry business highlights one-component polyurethane sealants and adhesives. Examples include Sikaflex 292i and other Sikaflex polyurethane adhesive/sealant products. Asia. Pidilite Industries, Mumbai, India. Pidilite is a major Indian adhesives maker. Its adhesive lines include Fevicol, synthetic white/PVA type bonding adhesives for wood, paperboard, laminates, etc., and Fevikwik, instant adhesive/cyanoacrylate type quick bond products. Toagosei Company, Limited, Tokyo, Japan. Toegosei's adhesive materials business includes instant/cyanoacrylate adhesives under Aran Alpha, plus light curable adhesives, reactive adhesives, hot melt adhesives, film adhesives, epoxy resin adhesives, polyurethane adhesives, and solvent-based adhesives. Shin-Etsu Chemical Company, Limited, Tokyo, Japan. Shin-Etsu produces silicone adhesives, including silicone pressure-sensitive adhesives for tapes and protective films, and silicone adhesive sheets used in construction and related applications. KCC Silicone Corporation, Seoul, South Korea. KCC Silicone states that it produces silicone materials through finished products and offers sealants for construction and industrial use, along with silicone product lines such as PSA/RLC and RTV silicone materials. Huitian New Material, Shanghai, China. Huitian describes itself as one of China's long-established adhesive/new material companies and lists products including photovoltaic adhesives, electronic adhesives, packaging adhesives, industrial adhesives, battery adhesives, silicone adhesives, polyurethane adhesives, and hot melt adhesives.